So, now when one tries to write a code, so one needs to give in some bare minimum amount of information or some amount of input. So, the input data that one will need to put in here for this to convert this to the code. So, what the first thing you need to know is what is the limit of integration. So, in general, for this particular case your x can go from minus infinity to plus infinity, but that is not possible to do for numerically. So, I need to give some maximum value up to which I want to do the integrate, some maximum value of x, which I call as x max. Then what we also need to do is to tell the code how many grid points one needs to use, because that determines how the value of delta x and also the accuracy of your calculation. So, delta x will then be given by x max by n, where n is the number of grid points. Then you need to tell code which particular solution you are looking for, or the number of nodes of required nodes. So, do you need a solution with 0 nodes? Do you need a solution with 1 nodes? Do you need a solution with 2 nodes? You need to give initial guess of energy, trial energy, and you also need to give a file name to store the wave function. So, this is what you need to have in the program. I mean, you need to give as input when you write the program. So, if you just use so whatever we have learned so far and try to write a program, we will see how to I mean, I will show you an example program, and there we will see the problem of the asymptotic behavior, which is not till now taken care of. But before we go there, maybe I will just show you the program and the result. So, what we saw is that the asymptotic behavior of my wave function is not coming correct. What I mean by that is, suppose this is my limits of integration for my harmonic oscillator. So, ideally for n equals to 0, ideally what I would expect is something like this, a very symmetric wave function which gradually decays to 0. But what you actually got from what the code actually gave you is this part is fine, but then after a certain point it starts blowing up, both this side and this side. So, in other words, my asymptotic behavior is not correct. So, the question is how to get the correct asymptotic behavior. So, to achieve this, what we will do is we will perform 2 integrations. So far we have been performing just one integration starting from x equals to 0 to x max. Now, we will perform 2 integrations. The first integration will be starting from x equals to 0 and integrate outward, and then the second integration will be start from x equals to x max and integrate inward. So, we start from so basically so if this is my potential energy and I am trying to integrate from this limit. So, this is my x max. So, what I will do is I will start one integration from x equals to 0 and move outward. I will start another integration from x equals to x max and move inward. So, this tells me that at some point these two must match. So, now the question is where do these integrals match? So, to match the integral, what we will do is we will choose the classical point of inversion. So, the matching happens at the classical inversion point, which I am calling as XCL. What does one mean by this? What one means by this is that at this value, at VXCL, my energies are same. So, and for x less than XCL, my E is greater than V, and for x greater than XCL, my V is greater than E. So, here we are going to the classically forbidden regime. So, this is a natural choice, and how do we match it? So, we match it in two ways. Matching should follow the following criteria. So, we will use two properties of the wave function. The one property is that at the classical point of inversion. So, if I call this psi r and if at psi l, so the psi r at x classical should be equal to this psi left at x classical is equal to psi x classical. So, that means my wave function is continuous, and the second condition is we also need to satisfy that the derivative, the first derivative of my wave function is also continuous, that is my psi 1 r at XCL is equal to psi 1 r, this will be L, psi 1 L at XCL equals to psi 1 at XCL. So, these are the two basic properties which any wave function should satisfy. This we learned from our first class in quantum mechanics. So, just to summarize how we do the matching is done by making sure that the wave function and its first derivative is continuous at the classical point of inversion. So far so good, but then there is another problem here. So, if you realize, I mean, we are doing a grid based method, it is not an analytical method. So, what that means? So, I am just drawing it. So, suppose this should be symmetric, though it is not very symmetric here. Suppose this is the particular energy eigenvalue which I am looking at, okay, and this is my exact. So, this is my x classical, but this is the exact value, but in the calculation what we are doing is, in reality what we are doing is that this x, so say from x to, and this is my x max, this we are dividing it into small grids. So, as a result what might happen is, as you see here, that this is my exact, maybe I use another color pen. So, this is my exact point of this classical inversion which is happening, but that point does not lie in my grid. So, either I have a point before that or a point after that. So, the accuracy in this case of determination of XCL is limited. If I have a smaller and smaller grid point, then the probability of this XCL, I mean having one of the grid points exactly at XCL increases, and that what it means is that the accuracy of determination of XCL is limited by interval between grid points. So, in this case, so basically the question is now how to find out the classical point of inversion. So, to do that, what we do is we find the first grid point where V x is greater than E. So, we call this particular grid point as ICL, the index I give as ICL. So, once we find that grid point, so that particular point, the x value will be given by ICL delta x. So, then what I know is that my exact classical inversion. So, my classical inversion point, that is where my quantum and classical the energy eigenvalue and the potential becomes same, that inversion point lies between x c minus delta x and x c. So, once I find this classical inversion point, so the next step will be I perform the outward integration from x equals to 0 to x equals to x c. So, which I am calling as psi L x, which is defined between 0 to x c. Just let me make sure that the nomenclatures are I am using the same. Okay, so, this will be r. So, let me just cut it. So, it will be psi r and this will be psi L. The outward is L, psi L, and the inward is psi r. So, while performing this equation, this outward integration, what I should also do is count the number of times my psi L change sign. Now, if the number of times my psi L change sign equal to the desired number of nodes, then it tells me that this solution is correct. If not, that is if n is different, we need to do is adjust energy. Okay. So, we need to adjust the energy using the same shooting method that we described before. Another thing to keep in mind is that in all the cases, your wave function will not have any nodes beyond the classical point of inversion, because beyond the classical point of inversion, that is in the region where the presence of the particle is classically forbidden, what the wave function should behave as an exponentially decaying wave function. There will be no oscillations in the wave function. So, hence therefore, we do not find nodes beyond x c. So, this is about the outward integration. So, once you are sure that your outward integration is correct, that is once you know that the number of nodes match, basically what it means is if number of nodes in outward integration is equal to n, which is my desired number of nodes, what I do is I start the inward integration, which I define as psi r x, and which is defined in x c x max. Now, once I have done the two integrations from 0 to x c and from x max to x c, then what I need to do is now match the wave functions, that is match my psi r and psi l at x equals to x c. So, how do I match it? So, as before, my wave functions should be continuous, and to do that what I do is I rescale my psi r, that is the value of the outward integration, by a factor which is equal to psi l, the ratio of psi l and psi r at x c. And once it is done, so what this does is ensures psi is continuous. So, once this is done, we need to normalize it, that is my mod psi x square dx, the integral over the whole range of x should be equal to 1. So, this goes the matching of the wave function. Now, if you remember, we also need to match. So, we have satisfied the first matching condition, that the wave function is continuous. Now, we need to satisfy the second matching condition, that is the matching of the derivatives. So, ensures continuity of my derivatives. Over the range. So, that basically means matching psi r at x c with psi prime l at x c. So, the ideal scenario is that my psi r prime at x c is equal to, or we can write it minus psi prime l at x c is equal to 0, but this is only correct, or you will get this condition only when you have reached the correct energy eigenvalue. Otherwise, you will not get, this condition will never be satisfied. So, and so to do that, what one needs to do is basically again go back and apply the Taylor series expansion till you get this condition is matched. So, for the numerical case, this should be of the order of this epsilon, which is 10 to the power minus 8, this difference. Okay. So, how to do that? To do that, what we do is we again apply Taylor series expansion. So, now what we are going to do is we are going to look into the sign of this difference. So, basically the sign of this quantity here and determine E. Okay. So, if I do the Taylor series expansion of my left wave function, that is psi l I minus 1, this is equal to psi I l minus psi 1 l I delta x plus half psi 2 l I delta x square, plus I have third order term here. Similarly, my the right hand psi r I plus 1 is equal to psi I right plus the first derivative of the right hand at I del x plus half psi I second derivative of right to del x square plus the third order term. Now, here you note one thing, that I have just written as a short form of my ICL, that is at this, all this thing is happening at the point of inversion. Now, from the previous part what we have seen is that at I, my psi I left equals to psi I right, because I already ensured the continuity of my wave function, this is equal to psi I. So, we put that in to this particular, so we put this values of psi L and psi R and psi I into this wave function. Also, you should note that the second thing is again at I, the second derivative L I is equal to the second derivative of the right hand side I, which I am writing as psi 2 I. The reason for this is this comes from the, this is my from my differential equation, right, based on the Numerov algorithm. Okay. So, what we do is now we plug in these two things into these two equations and we take the difference, we will just add up these two equations. So, we plug in, so here instead of psi L I, I will put psi R I put psi R I, and again these two are also same, and then if we add, what I get is the following. So, psi I minus 1 L plus psi R I minus 1, this equals to psi I, both are same and I am adding. So, I will get 2, then I will get plus psi I 1 R minus psi I 1 L into delta x plus, again these two are same. So, it is just twice this. So, that will be psi I second derivative delta x whole square, and then we have the output. So, if I simplify this, so what I will get is now psi. So, what I want is to compute the difference between the derivatives of my wave function from the outward integration and from the inward integration at the inversion, classical inversion point. So, that will be given from this equation. So, 1 R minus psi 1 L at I, this is equal to psi I minus 1 L plus psi I minus 1 R minus 2 plus f I delta x square. So, how do I get f I? I get f I because this is from the Schrodinger equation itself. So, I have my Schrodinger equation psi double dash equals to f psi. So, from there I have just put in plugged in the value of psi double dash into this one divided by delta x. Now, if I let us assume y I equals to 1 minus, as this is as before, we have done the similar assumption before. So, what I get is delta x square f I equals to 12 minus 12 y I. So, if I plug this thing here, so at the end of the day what I get is the difference between the first derivative of my inward and outward integration. This is given by psi I minus 1 L plus psi I minus 1 R minus 14 minus 12 y I psi I divided by delta x. So, this thing, so this particular equation, this basically what it does is it, so it is a measure of discontinuity in the first derivative of my psi. So, now looking into this the sign of this particular quantity, I can judge whether my energy has been I mean my initial guess of energy is higher than the actual one, or the initial guess of energy is lower than the actual one. Accordingly, I change my bracketing region and then I zero down to the correct value of energy. So, the way to do that is, if my sign of psi 1 r at I minus psi 1 r at sorry, this will be L at I. If this is positive, this typically implies that my energy is high. So, what we need to do as before is move towards lower part of the bracket. If sign of psi 1 r I minus psi 1 L I, if this is negative, this imply energy is lower than actual. So, this is higher than actual, and then what we do is we move towards higher part of the bracket, and then we repeatedly go on doing this till we reach the convergence. Now, so far so good. Now, one thing is still left, is that now the next question is for, so we know how to work or how to set the initial conditions, the two initial conditions for my outward integrations, that is when I am going from x equals to 0 to x c, but we have not talked about what is the initial, what should be the initial conditions for the inward integration, that is when we go from x equals to x max towards x equals to x c. So, that is what I will just briefly describe now. So, for inward integration, what are the initial conditions? So, this is what I am going to talk about. So, suppose I have at x equals to x max, if this wave function I call as psi k m. Okay. So, I need two initial conditions. So, by definition, since this outward integration I am already in the classical forbidden regime, and my wave, I know that my wave function should decay exponentially, and if by x max this one is quite large. So, it is safe to assume that the next point after this x max, the wave function is 0. So, the first initial condition I set to is psi at x max 1 equals to 0, and then psi at x max, this I set to some small arbitrary value, which is I call dx. So, once I know that, so what I do is I use this equation. So, earlier what we did is, for the outward integration we need to know k minus 1 and k, and we go to k plus 1. Here what instead we have to go the other way around. So, what we know is k plus 1, we know what is k, and we need to find out is k minus 1. So, we need to rewrite my Numerov algorithm in or the Numerov equation in a certain way. So, this is my Numerov equation, which I have been using for my outward integration. So, now what I will do it is I will rewrite this in terms of y k minus 1. So, what I will do is I will take this to the left hand side, then bring this product to the right hand side and this to the left hand side. So, if I do that, so what I get is psi k minus 1 y k minus 1, this equals to psi k 12 minus 10 y k minus psi k plus 1 y k plus 1. So, therefore, my psi k minus 1 is equal to psi k into 12 minus 10 y k minus psi k plus 1 into y k plus 1 divided by y k minus 1. So, this is how I will proceed. This is for my inward integration, that is from x max to x c. This was for my outward integration, that is 0 to x c, and these two are my initial condition for inward integration. So, note that for the initial conditions for the inward integration, we did not need to use the property of the parity of the wave function and so on and so forth, because the reason for that is we know that in this case the integration will always die down to 0, because for the regime outside the where the particle is classically forbidden, there we always know that the whatever be your problem, the quantum mechanical problem, for all bound potentials, the wave function should always decay down to 0. So, this is quite more general in that sense.